All right. Polyprotic acid-base equilibria. So we talked about monoprotic before, now we're doing polyprotic. Polyprotic is not difficult. It's literally doing monoprotic several times, right? That's all it is. Because remember, by definition, an acid has to lose the first H+, right? And to get the second H+ lost, you then lose one. Then you can lose the second one, right? So the order of operations is maintained. Does that make sense? Okay. So polyprotic acids and bases are going to be those that can donate or accept more than one proton, but remember again, they always have to do it as an order of operation, one at a time, right? You can't do it two at a time, by definition. Diprotic acids, therefore, can either donate or accept two protons. So these are some different polyprotic acids. Right here we see things like amino acids, like alanine, right? They can have two hydrogens attached to them. Those are charged diprotic acids. Everybody's aware of that, right? You can put a proton on the amine portion of the amino acid, and they can be doubly protonated, and that would be a diprotic acid. There's also the neutral diprotic acids. These are going to be things like sulfuric acid and carbonic acid. Those are probably your most common examples, right? The ones you guys would know the best. Here we see a neutral triprotic acid, which is phosphoric acid. Okay. Everybody good with that so far? Yes, you can have charged triprotic acids, and these are the useful ones that are relatively small molecules, but like a protein, large proteins can sometimes be many protic acids, right? A very large polyprotic acid, okay? So it doesn't end at triprotic acid, that's not really useful after that point, just polyprotic acid, right? Common classes of diprotic acids are going to be amino acids. These are one of the most common classes of diprotic acids and probably the most useful one to understand because they're amino acids, right? They're the building blocks of life. Lots of stuff going on with those. These also have a carboxylic acid group, a basic amine group, and a variable substituent that we designate R, some of which are acids or bases, right? Like the amine ones are bases, right? The ones that are protonated are acids, like there's carboxylic acid as an R group. Or we can have a protonated amine, right? Okay. The carboxyl group is a stronger acid than the ammonium group, so the non-ionized form rearranges spontaneously to the Zwitter ion. What does Zwitter ion mean, by the way? Okay, Zwitter means two-handed, by the way, in case you're wondering. It means two. Like Zwitter sword would be a two-handed sword. So like a great sword in German is Zwitter. Anyways, Zwitter ion means two ion, right? So it means you have both positive and negative sites on the same molecule. It self-deprotonates, right? It self-acid bases. It acid bases itself. Sounds like a rave or something, doesn't it? All right, so right here is an amino acid. This is the neutral form. That doesn't exist in solution, does it? What happens? The carboxyl group is going to donate a proton, right? The amine group is a weak base, so that's going to accept a proton. Yes, if you're wondering how the hell it donates the proton to itself, like is that thing popping off and then like traveling through space? No, it doesn't do that. It donates it to water water donates hydrogen to this, okay? So it doesn't actually donate to itself. That's just something to help you remember, right? Okay. So that's the substituent, of course, the R group. You all know that because you had my biochemistry. The ammonia group is going to have a pK of 9.5. It's basic. In neutral water, it's going to get a proton on it, right? It'll act as a base, giving you conjugate acid. The hydroxide group is going to have a pK of 2.5. So pH is like 2, 2.5, it's going to be protonated, right? pH is above 2.5, it's going to lose its proton to the solution. Anybody have any questions about that so far? So essentially, all pH ranges between 2.5 and 9.5, you're going to have the zwitterion, essentially, right? As your predominant species. As you move closer to one of those points, you're going to start having it either take on a proton in the carboxylic acid or lose the proton from the amine, well, ammonium salt in that case. Anybody have any questions about that? Okay. Don't forget these R groups. Some of them are charged and some of them are acids and bases, right? So that does, you can have a charged triprotic amino acid, right? That exists. That's a thing. They're quite interesting. You can get lots of stuff. Right here, this is your acid dissociation constants for all your different amino acids. You can see you have a carboxylic acid pK, which is always low numbers, right? They change a little bit because you have different substituents causing those charges to change. Note that there's actually some really interesting ones here. Like this one right here is very interesting, right? Histidine. Isn't that kind of cool? And then you have things like tryptophan and stuff that wrap around back on the amine, right? And bond to it and stabilize that amine. So histidine, tryptophan, these all have very interesting properties. Anyways, keep in mind these substituents, they do have pHs for things like this right here, arginine, right? See, arginine's quite an interesting base. Isn't that cool? Come on, you gotta love it. Look at that arginine. You ever seen a base like that? Now you have. Appreciate it. Love it. Come to the dark side. All right. Now, here we see the acid going to base forms. See that? This is a useful way of thinking about these triprotic, polyprotic acids and bases, okay? You have essentially multiple species that exist between different ranges in the predominant form. Again, don't forget that as you get closer to pH 2.3 here, you're going to increase the amount of the conjugate acid form, right? Okay? But until you get to that pH near 2.3 something, this is going to be your predominant form, zwitterion. Okay? Anybody have any questions about that? Anything not clear? Right, very good. What is it called when it can both act as an acid and a base? So if it's an acid only, it's called an acid, right? If it's a base only, it's called a base. If it can act as both, it's called ampiprotic, meaning both. Right? Ampi meaning both, protic meaning proton, right? Take on and lose a proton. Okay, these are some of the leucine one. Do you guys have any questions about this, or are we good? I think most of you, like we do a whole couple chapters on this in biochemistry, and you've learned this material in Gen Chem and Organic 1. And so I think most of you are like, yeah, The only part that's anything challenging would be the math. Again, if you have a diprotic system, you're going to lose one proton. That first proton will have a Ka. That is a larger number than the second one, right? Because it'll lose it easier. It is a stronger acid. Losing the second proton will be much more difficult. Typically, it's something around a 10 to the negative 6, like a factor of a million difference. Okay? But some of them are less and some of them are more. You can have factors of 1,000, factors of a billion difference. This is mostly due to things like the fact that this one's charged, right? So this first one comes off really easy. The second one is no longer charged. It comes off much more difficulty. That making sense? Fantastic. So this is actually a zwitterion, isn't it? Because around pH 7, it would lose one proton and gain one proton, right? And that's told to us by these numbers here, isn't it? This one's an acid, it's going to lose a proton. This one's a base, it's going to gain a proton. Note, however, this zwitterion here, which is the amino acid, it is overall neutral as the zwitterion, right? So its overall charge, it's non-charged, neutral, zero charge. Even though it has a negative and a positive, right? So calculate the pH following a 0.05 molarity aqueous solutions. Leucine hydrochloride, sodium leucinate, and leucine. Okay, so the hydrochloride version, what do you think that is? Anybody remember that? So when you see a species like leucine, so it's amino acid, leucine, it could be a drug, it could be anything, okay? And it's followed by a dot or HCl or by hydrochloride. It means they've added enough acid to fully protonate it. Okay? Okay. What would be the sodium leucinate? They put sodium hydroxide in there until they made the salt, didn't they? There you go. There you go. Leucinate being the conjugate base, right? The anion form. Sodium being the metal ion that makes the salt, right? Okay. And then what would leucine be? That's just the natural amino acid, right? The zwitterion form. Yeah. So you got the acid, the base, the zwitterion, don't you? Okay. The pKs of this are going to be 2.328. That's going to be the leucine hydrochloride, the acid form, right? 9.744, that's going to be the sodium leucinate, right? That's going to be this form. And then this one's going to be a combination of those two, which is essentially a buffer system, isn't it? So again, this is the acid form. It's going to have a positive charge, so H2L, right? L standing for the leucine. Notice it's taken on an extra H+. That came from the hydrochloride, right? If you made this into a salt, by the way, it would have a matched Cl- that would come with it to make the crystal. Okay, this right here is the sodium leucinate. It's going to dissociate when it dissolves in solution, right? So you get the L- form. Right here, this is the leucine. This will be the HL. It has an H on it because it has that on the, well, it'll be on the ammonium, right? The amine portion of it. So first thing you should always go ahead and do is you should always go ahead and sort of estimate your answer whenever you do these problems. And then you should calculate it. This is going to keep you from getting in trouble. You estimate your answer based on the facts of the matter, then you can always aim for something, right? So your weak acid, H2L+, this is going to dissociate only a little, and an even weaker acid, HL, will dissociate hardly at all. This here we know is a factor of 10 million difference, right? So there'll be 10 million times less of the HL dissociating than there is H2L. It's not going to change your number, is it? No. If they're a factor of 100 difference, then probably not going to change your number or anything significant, is it? All right, so we can treat this as a monoprotic acid. We don't have to do any extra work because, I mean, only one of them is going to really matter here. The other won't change our answer at all. So just ignore it. So for reaction H2L+, dissociating to give us H plus and HL, we can set up and solve our equation. Which equation? Well, it's a weak acid dissociating, isn't it? So we just have to use our Ka expression. There's the full one, which you could simplify yourself, or there is the simplified one here. So we can type it up ourselves. You know, we have the H plus times the HL, right, on the product side, divided by the H2L plus, which is on the reactant side. This is X for each of these, and the bottom one is what we put in, minus X, right? Again, we would expect this X value to be much smaller than what we put in, so we can assume that this minus X doesn't need to be done, right? Our F value is this number we were given, 0.05. Our Ka is 10 to the negative pKa, right? So we just take 10 to the negative 2.328, multiply it with 0.05, take the square root, and that would give us X. There we go. Anybody have any questions? Did I lose anybody? It's the same problem we've done like 4 or 5 of, right? Okay. Okay. You can solve it using the quadratic equation, but it probably is not. Oh, I guess this one would be necessary. So remember, when you go to the bottom here and you get your X answer, this always needs to be at least a factor of 100 smaller than this number here, right? If it's not, what do you have to do? Solve it using the quadratic formula, right? So this would be A here. Whatever's in front of. Okay. So you'd have to do the A, B, and then you'd have to figure C. So if you make the assumption, okay, so the quadratic equation is to solve something that has an x squared plus x plus c equals 0, right? You can't solve x without the quadratic equation or a similar formula. There actually are alternatives, by the way, in case you're ever curious. There's actually supposedly a quadratic-like equation that's easier to use. So you can look it up sometime if you want to try it. But you can't solve for x in this formula right here directly, can you? See that? Because you'd end up with x squared and x, wouldn't you? And they don't directly solve. So there is an assumption you can make here, which is if this x is small enough, it won't change this 0.05 number, will it? Like if you had an x value that's 0.000001, if you subtract it off 0.05, you're just going to round it right back up there, aren't you? So it wouldn't change it. Okay? If this was something like a 6, 5, that would be true. But because this number is a -2 up here, it's not going to be true, is it? You can see that from this number here. That's 0.01. 0.05 minus 0.01, that's a significant change, isn't it? And so you can't make that assumption. you have to keep the minus x because it significantly changes it, right? Okay, let's do a more real-world example. You're paying $100 for something at the grocery store. Can I go, yeah, I'll need to give you 20 bucks? Are they going to accept that? No. They're going to tell me give them the damn 20 bucks, right? Okay, how about if I'm 1 penny short? Yeah, they're going to probably just take a penny out of the give and take a penny jar and whatever, right? In fact, most of the people just, I don't care, whatever, 1 penny doesn't matter, right? Because again, you essentially would round it back up. And your bank does that all the time, you know that, right? You didn't know that? So every time they do transactions, move money, do interest, anything at a bank, they always round it in their favor by fractions of a penny. And if you actually add all that money up, there's been computer viruses that steal that money. The one that's probably the most drastic example happened like 20, 30 years ago. And in a single day, it gathered $400 million. So the banks are actually stealing a lot of money from their customers by doing that. But, it's not significant enough. They get rounded off all the time. And so nobody knows. It's just that they're doing it in their favor all the time, and that's why they're stealing that money. In random numbers, it's not in your favor all the time, right? It fluctuates back and forth. So you end up canceling overall.
So if the F value was like 5 times 10 to the negative 8 or something like that, and the X would
Well, then it would really matter. If the F value here was like 50, then this X value wouldn't matter at all because it's 0.01. Yes, the smaller your X value is, the less it matters, right? The larger your F value is, the less the X value matters, right? Because remember, you're talking about how much of it disassociates. So if none of it dissociates, essentially, it doesn't change your starting concentration, does it?
So at what point does the X not really matter? Is it like once?
So the Gen Chem cutoff was 5%. If this value is less than 5% of this value, that would be where you can make that assumption you're okay. That's actually not a good way to do it for these problems. What you're looking at is if it's outside of your range. So like if you have an uncertainty of plus or minus 0.01 here, then this would have to be something significantly less than that. So like a 0.001, right? Make sense? Like you want it to be, ideally it would be a tenth of your significant figures.
That's just something that you would assume at that point. You're like, oh, I think.
Yeah, I mean, if you're less than a tenth of where your uncertainty is, it's not going to change at all, right? You'll round it right back up, it won't matter. And that cutoff is not exactly, if you're unsure of that cutoff, do the full calculation, okay? Because it's not immediately sure all the time. And it's always correct to do it the full calculation. You can always do it the full calculation. That is always correct. The assumption is just to make this faster. Okay? Okay. Does anybody have any other questions? Or more questions on that? Okay. Keep in mind that when it comes down to things like analytical chemistry, an analytical chemist is a master of uncertainty. They understand where the uncertainty cuts things off, and it no longer benefits them to take more time to do stuff. Okay? That's the reality of a good analytical chemist, is they know where they can cut corners and it won't matter. Because their uncertainty masks it completely. Okay? Okay, anyways, that gives you a pH of 1.88. I'm sure you're not particularly surprised it's somewhere near 2.3, right? Yeah. the pHs are always going to be somewhere around the pKa's. Again, here we have a diprotic buffer. And so, again, yes, a diprotic acid can make a buffer system. They're actually quite good at it. And you can, in fact, make two different buffer systems, right? Because you have two different pKs.
So how exactly does it work as a second buffer system? Like, if you want to use it for like a base.
Okay, the best thing I can tell you about diprotic and triprotic systems is think of them as regions. So remember the graphs we always talk about, where as we add titrant, we get the buffer system, and it rockets up, and that would be our pKa, right? And then for a diprotic system, this levels out to a new buffer system. And then it rockets up again. And then it levels out, which is, we have base being added, and our top is whatever our base is. Okay, when you think of those, think of them as regions that species dominate. Okay? So at our most acidic point, our most acidic species is dominant. As we go into our buffer system, we get halfway there. We're going to be at pH equals pKa, right? And that's where we're 50-50. As we go beyond that and get to where it peaks, that's going to be our medium species, our second deprotonation. Okay? So we'll have the HL in this case being the dominant species. Once we go past that, we're back in a buffer system, right? And the buffer system, again, is going to be decreasing HL to make the H2L, to donate the H and make the L minus.
So it works both at like the pKa and at the base, and then at acid section 2, or?
Think of them as regions again. Okay, so you're deprotonating the first proton. When you get to the middle of the buffer region, that means you're 50% done. Okay? You've deprotonated 50% of the first proton. You have to deprotonate all of the first proton to get to the second one. Okay? They don't overlap. Remember we were talking about different salts where we could precipitate them? Those overlap. These don't. Because you have to deprotonate the first proton to remove the second proton. You literally can't do the reverse, ever. You know why you can't do the reverse? Because you're literally reacting with something that takes a proton. So if it's going to take a proton, it always takes the easiest one first. So it can't take the second, can it? And you never get three things colliding in space at once, do you? There's just very little chance of that happening. Okay, so again, think of it as regions, right? Deprotonate the first proton. Middle of the buffer region is 50%. Everything above that 50% is, we have more and more of the conjugate base, the second proton, okay? And then we completely overwhelm it, we're done with it, right? That's where it goes up really fast. And then the next portion is going to be taking off that second proton. And again, when you take it off, it's going to get closer and closer to 50-50, which is a buffer system, right? And then once you completely, you keep removing that second proton, you're going to get to the fully deprotonated version, right? And that's where it goes straight up, because it doesn't have any more protons to get. All right. The first one goes straight up because it takes a while before the second one is willing to come off, right? Is energetically favorable to come off. Does that make a bit more sense?
Yeah.
It's a very systematic system, right? Very systematic, very definitive. Okay? Of course, that's for a single diprotic system, right? If you have more than one, like if you have multiple different amino acids, then you can start getting more complex behaviors. Okay, but a single amino acid, you just look at the species, and they're going to be very regimented. Okay, so let's calculate the pH of a weak diprotic bases. Again, these were the base forms of it. Again, that's just going to be flipping that graph, right? So you're going to protonate one species, get the other species, and then you're going to protonate that species to get the third species. Okay? So the weak base, L minus, ionizes by hydrolysis only a little, and even the weaker base, HL, is going to ionize hardly at all, right? And remember again, that's because there's usually a factor of like 1,000,000 between one ionizing and the other ionizing, right? Even the ones that are the closest together are typically factors of 1,000. So you'd have 1,000 times the L minus as you would the HL. Okay? There's quite a bit of difference between them. All right, so in many of these diprotic systems, you can simply treat it as, if you start off on one side of it, you really only get one proton on, right? And then the second proton you're never going to get to. It's just too far away, too energetically different. That making sense? Fantastic. Okay, so again, when we do this problem, if we're doing it for a monoprotic base, we do it just like we would for the diprotic acid. We do it like it's a monoprotic base, just like we did a monoprotic acid before. We take the Kb, that's the HL over OH minus over L minus. By the way, it's going to end up the same thing because all of your species deprotonates, is deprotonating, and that's the only form of the HL you get, right? So it'll end up as x squared over what you put in minus x, right? Okay. Again, you then need to solve. In this case, we have 0.05 molarity for our F. The x's, of course, stay there. That's what we're solving for. And we have a Kb of 5.55 times 10 to the negative fifth. Okay. This Kb actually tells us we probably could assume this x right here, that we don't have to subtract that off, and we could probably get a good answer out of that. Okay? We can solve it always using the quadratic equation. That's never a problem. You can always solve it with the quadratic. So if we solve it, we get x equals 1.64 times 10 to the negative 3. That's on that cutoff point where I would use the quadratic equation, okay? Because that would be this last digit, see that? And that means we're well above 1%, right? Now, we may be below 5%, but I don't like 5% rule for analytical chemistry. That's a terrible rule to use. Because, I mean, we have uncertainties that are well within 1/10,000th, right? 5% would be awful. Again, you'll get an OH minus concentration. The easy way to get into pH from there is to do the negative log of the OH minus and subtract it off of 14, right? Okay. So a molecule that can both donate and accept a proton is going to be called amphiprotic. This is going to be the mid-range of your diprotic buffers. So your diprotic buffers, that middle species, is always amphiprotic, right? It can take on a proton and it can donate a proton. This is going to be the part that's a little bit more difficult, okay? Oh, okay, let's call that a day, and we'll pick up from here next time.